Hi everyone, this is going to be a lecture over dimensional analysis. This is in our practical pharmacology book for the surgical technologists, and this should be review. This is a throwback to math. It's going to be great. So according to the book, dimensional analysis is used to describe the process of understanding and applying the relationships between the qualities of various items. And some of those items could be drugs and systems that are used for identifying and measuring drug dosages, let's say. And that's going to be based on the physical characteristics of each item. And some of those characteristics that we consider important as surgical technologists is the weight, the size, the distance, and the time between these systems. When I hear these different comparisons, it makes me think of the steam sterilization process when we talk about time, temperature, pressure. All of those things are physical characteristics that allow us to achieve sterilization, right? So definitely those things are applicable here. And so like I said, this is just going to be a quick review of basic math. Everything that this chapter goes through is just an extremely condensed version of the applications of math course that we have already had. But it's really important for us to understand numbering systems and be able to calculate drug dosages and concentrations. It's also important for us to be able to use basic math to perform counts correctly, and also to verbalize medications or irrigations that have been used. In addition to that, there are a variety of symbols that are associated with basic math, and they are in the text. You can look at them there, whether they're percentage, plus, minus, equals, greater than, less than, division signs. All of those we're pretty familiar with, and the text also gives some good definitions of basic math terms as well. So fractions, remember way back when we talked about fractions, we converted them, we multiplied them, we divided them, added them, subtracted them. We did everything that we could possibly do with fractions. A common fraction would be one that is like 1/2 or 1/4 or 3/4 or 2/5, anything like that. But then we also, remember, we have those compound fractions as well, which has a whole number and then a fraction kind of squished together, like 2 1/2 would be an example of that. And so typically in the operating room, you're going to see fractions displayed as percentages, right? Think about our local anesthetics that we use in the operating room. For example, 0.25% marking with epi, all right? Or 1% lidocaine with epinephrine. And then it's also important to remember when we are writing decimals, and you guys know that this also represents a fraction, but one of my pet peeves is leaving the 0 off from the front, from before the point. So it's really, really important from a documentation standpoint and just to limit the number of errors or misreadings that we put that 0 in front of the decimal if we have like a 0.5 or a 0.25. Let's go ahead and write that out when we're labeling our medications. Moving forward, some variations, like I said, in fractions, there's that simple fraction, 1/2, compound. We have a whole number that we have squished together with a fraction. There's also complex fractions. We've worked with all of these. For it to be considered a proper fraction, remember the numerator needs to be smaller than the denominator. So 1/3 would be proper, but 3/1 would be improper, or the example here is 3/2. And then we have those mixed numbers as well. And then there are equivalencies, right, of fractions. So if we look at 6/10, we can see that there is a number that would go into both of those, and that number would be 2, right? 2 goes into 6 3 times, 2 goes into 10 5 times. So then we could reduce that guy down to 3/5. Is this ringing some bells for you guys? So here's a good reminder and image to go along with the decimal system. Remember when we're reading it from left to right, we have our whole numbers to the left of the decimal, and this image starts in the millions, and then the 100,000s, 10,000s, thousands, hundreds, tens, and ones. And remember to put in those commas, that's extremely important. And then to the right side of the decimal point is going to be in the first place to the right are tenths, and then our second place is the hundredths. My dogs are yapping away, I apologize. And then to the far right here on this image, we have the thousands, all right? And so that is representing a fraction of something, right? Not a whole, but a part of something, whatever that may be. All right, so percentages are written as parts of 100. Remember, so if we dig back in our brains to math, we remember that we would set a number over 100 to depict that it was a part of 100. So 25 over 100 would be 25%, right? We can also express it as a decimal by moving the decimal point left 2 places. Now ratios, remember ratios express relationships between two numbers. So let's say the ratio in our lab class is 10 students to 1 instructor, or 1 instructor to 10 students. So that would be a 1 instructor to 10 student ratio, or a 1 to 10 ratio. And we use the colon to separate those numbers. And we would always want to reduce that to the simplest terms. But it can also be displayed in different ways, as we have seen. Now, proportions, the terms of ratios must be labeled. And remember, when we set up proportions, we would set up 2 fractions separated by an equal sign. And, we would set the percentage over 100, and then there was a portion of something, and we were trying to find the other number to equal out the proportions, right? So there's going to be an unknown term that we're looking for, and then we did that cross multiplication and divided to get our answer. Now, a lot of times we see Roman numerals being used for numbering, and so some of them are listed here. The I is representing 1, where the V represents 5, X is 10, L is 50, so on and so forth. Roman numerals, remember, are read from left to right, and numerals placed to the right of a larger number add value. All right, so if we had like VI, for example, that would be 6. But if we have a lesser value placed to the left, then we're going to subtract. So in the flip side of that example, if we had IV, then that would be 4, okay? So then there's also an order of operations. When we are identifying Roman numerals, we want to first identify and perform all subtractions, then add the remaining values to get our answer. So remember that military time uses a 24-hour clock, while our standard time uses a 12-hour clock, right? If we just look at the face of a regular clock, we see the numbers 1 through 12, and there's that distinction between AM and PM, or ante-meridiem and post-meridiem. So military settings looks at the day in 24 parts instead of 2 parts of 12. Okay, so using military time helps us to mitigate the confusion that could come with a 2 a.m. or a 2 p.m., right? Maybe that A looks like a P, or the P looks like an A, or maybe the AM or PM didn't get added. So this helps us to reduce confusion and documentation errors. Remember, it's written as a 4-digit number, and I put a chart here for us so we could look at it as I kind of chatted about it. And we can see that 1 a.m. is 0, 100 hours. And then we just kind of count 200 hours, 300 hours. And then when we get to 12 p.m., we're at 1200 hours. And then we continue. 1 p.m. is the 13th hour, right? 2 p.m. is the 14th hour, so on and so forth. And we do not put a colon between, right? Notice how that is missing as well. Okay? So here we're talking about international units, or IUs. They might also be called unit. So international unit, IU capitalized, or unit is all referring to the same standardized measurement of a biological potency of a drug. How strong is it? How much of the good stuff is there? All right. There is no conversion from units to other types of measurements and vice versa. So we can't convert units to milliliters or milligrams or anything like that. Some things that we want to think about with units, and I put this image on here for you of vitamin D3. It says there's 2,000 IUs, and you'll notice that the number 2,000 is written first, and then there should be a space, all right, and then there is the abbreviation for international units, all right. The standards for the international units are a product of the International Conference for Unification of Formula, and they also got some help from the World Health Organization. The Pharmacopedia, or the United States Pharmacopedia, the USP, has come up with a verified mark that the drug preparation meets these consistency standards. And some things that they look at are the purity, the quality, the strength, and the manufacturing process as well. Now, milliequivalent measures is represented by this lowercase m, capital E, lowercase q, milliequivalents. And a milliequivalent is a unit of measure, and that represents 1,000th of any measure. So if we had a drug that was measured in grams, for instance, then a milliequivalent would be 1,000th of a gram. All right, and here there is an example of potassium chloride, and you can see that it's 30 milliequivalents. Now, the apothecary system is old and antiquated, and apothecaries are what, in the olden days, pharmacies were not called pharmacies, they were called apothecaries. And so the apothecary system is a system of measurement, like I said, that is very old. It originated in ancient Greece, and it was used by physicians to prescribe medicine and formulate compounds. But it wasn't very consistent when we're talking about grains, scruples, drams, and so on and so forth. And so they decided that they needed a more precise way of measuring, and then the metric system was born. So in the United States, we primarily use the household system to determine length and weight and volume. So here we're talking about inches, feet, yards, ounces, pounds, tons, teaspoons, tablespoons, ounces, cups, pints, quarts, gallons. Think about you're in your kitchen making a cake or something like that, and it calls for 1 cup of flour. But the United States is pretty much the only place that this is used, and the healthcare system has adopted some use of the metric system, but sometimes even in the hospital setting, we find that some household measurements might be used when concocting like oral and rectal preparations that don't require exact and precise measurements as the metric system would provide. Interestingly and sadly, the mixing of the two in the healthcare system can be deadly, especially when we are talking about pediatric patients. Think about the conversion of pounds to kilograms or vice versa. That could give a very different dosage calculation if someone were to mistake one for the other. I guess you guys know where my feelings lie. Just think that there are some systems, some electronic medical records systems that will automatically convert pounds to kilograms, but some don't. And I really do feel like a more thorough standardization would be extremely helpful in regards to safe patient care. So the metric system is an international system of measurement, and it came to be in the late 17th century, and there were a lot of different individuals with many different ideas of how to create a standardized international system of measurement. So in 1790, the National Assembly of France made a formal request, and they came up with a system of weights that couldn't be disputed. And so this metric system came to be, and then consequently, the French government mandated the use of it. And because of the standardization and accuracy of the weights and measurements, that made the metric system well suited for scientific uses such as engineering and advances in industry. And so there were various other treaties that kind of either tweaked or revised, and they added temperature, which was the Kelvin measure. And there's a conference that still meets regularly to kind of revise and review the standards and to continue improvement of the system. But we call it the metric system. And there are some common measurements on this chart here, and you can see this kind of stair step. I liked this image just to kind of remind us how this metric system has these step downs from kilo being 1,000 down to milli being 1/1000th, with taking away 1 0 every time we step down, which kind of helps us with the conversion process. Commonly in the operating room, we're going to work with milliliters as surge techs, so you're definitely going to see that a lot, and you're going to be reporting fluids in milliliters for sure. So when we're talking about length, that is the meter in the metric system, and then weight, we're going to look at grams, and as far as volume, we're going to be talking about liters. So those are the three most common units of measure that are used in the medical setting. So some suggestions when we're documenting and we're using the metric system is to remember that 0 is placed at the left of the decimal if we have a quantity that's less than 1. So say we have 0.5, then it would be 0.5. And then the unit of measure is going to follow the number. We have to have our units of measure, or that 0.5 means nothing without that unit of measure. And we want to try to provide enough space between the number and the unit that it is legible, and so that there isn't any misinterpretations of the documentation. And then writing out or abbreviating a prefix or a unit. It just depends on, like a lot of times we do abbreviate those, but it could depend on hospital policy as well. And then we don't want to leave a 0 at the end of a decimal. So if it's, we're doing a conversion and we get 0.50, we don't want to leave that 0 at the far right. We would just put 0.5. And then a reminder that a milliliter is equivalent to a cc, or a cubic centimeter, but we're going to use milliliter or ml when referring to volume instead of cc. All right, so do you guys remember when we went over temperature conversions from Fahrenheit to Celsius and Celsius to Fahrenheit? Well, shake out the cobwebs. Here are the formulas that we can use to do those conversions. They've actually simplified it by turning the fraction into a decimal, so that does make it a bit easier to compute, to calculate. But the way that we remember our order of operations, I thought it was important just to circle back around and remind you guys of PEMDAS. And PEMDAS, remember, helps us with the order of operations of things. So we always want to start with whatever is in parentheses first. And then if there's any exponents, we want to take care of those and then multiply and or divide, and then lastly finish up with our addition or subtraction. So if we look at the Fahrenheit one, that portion that is in parentheses, we want to go ahead and take care of that first. So that would be our first order of operations. And since there isn't any exponents, we don't have to worry about that. But there is a multiplication or divide. So then we would want to take care of that next. And then finish up with our addition or our subtraction, which is not in the Fahrenheit to Celsius conversion, but is in the Celsius to Fahrenheit conversion. So just a little reminder, PEMDAS can help us remember those orders of operations. There is a possibility that you may need to do one of these conversion problems on your certification exam. So just some tips about dosage calculation. First off, I just want to say, I know that we performed several dosage calculations in our math class together. In the traditional role as a surg tech, though, I have not had to perform too many dosage calculations, but some things that dosage calculations are based upon, and, significantly important for us to have an understanding of the who, what, where, when, why. First off is the weight or the body surface area. And then secondly, the action of the drug. And then we need to look at the patient themselves. Can they metabolize the drug effectively? Do they have any drug sensitivities, or do they have any drug tolerances, right? The more we take a certain drug, the higher of a tolerance we build up. So, at first, if we have some knee pain, 2 ibuprofen might be sufficient. But after we've been, treating with that for a few weeks or a couple months, then it might take 3 ibuprofen to do the job that the 2 used to do. So that's something that's important to look at. And then, of course, the age and then the sex of the patient as well could be a factor. Additional things, genetic factors is definitely something, again, going back to the physiology of the patient, and then also thinking about what other types of medications is the patient taking, and could the one that they're looking at adding on have a possible interaction with those drugs that the patient's currently taking. And then there's that maximum dose, right? We calculated maximum doses in our math applications class. And so we know that there is a maximum. And that's an important conversation to kind of turn your ear into, because many times the surgeon will ask the anesthesiologist, how much of said drug can I give, right? And, if it's some sort of local anesthetic and we're passing that local anesthetic to the surgeon and refilling the syringe when it's empty, we need to be tuned into what that maximum dose is. If the anesthesiologist says, well, you can give 60 mLs and we're just passing over the 6th syringe, then we need to say, this would be 60. And not just continue to refill it, as part of our responsibility as an advocate to the patient. And then also the patient's activity level is going to come into play, right? The more we're up and around and what our metabolism is, and are we burning things off, and the fitness of our body and our organs and those kinds of things. Something else is the time and route of administration. So if we take a pill, it's got to go through the digestive system, and it's going to take longer to get to do what it needs to do, because it has to be broken down by the digestive juices in the stomach, and it's got to be absorbed and all of that. But if we inject it right into the circulatory system, then the effect will be almost immediate. And then, of course, that that plays into the hepatic first pass effect, right? So if it is ingested, then it is going to take a pass through the liver before it goes anywhere else. And then they would also consider any comorbid conditions that the patient might have. So sometimes medications are mixed or combined, and what is usually mixed is an additive. So an additive produces one of two types of effects, either a synergistic effect or an agnostic effect. Right, so the synergistic effect means that the additive is going to work with one or more other drugs that it's added to enhance the effects of one of those drugs or more of those drugs. An agonist, on the other hand, can stimulate or prolong the action of another drug or a naturally occurring substance, let's say, but they don't have an independent action. All right. Now, additives can also be used to dilute a medication, reconstitute a medication, or activate a medication. They can also serve as a preservative or give a flavor to something. I prefer grape. Or alter the pH of an initial drug. Sodium bicarb is something that sometimes they will add to local anesthetic, and it takes some of the sting away. So if they have little ones and they need to get like an IV or some sort of injection, an IV, typically they'll like numb up the little area before they put the IV in, and they'll add some bicarb to the local so that it doesn't sting as much. But when medications are combined, there is always a possibility that there could be an incompatibility. And so some signs of incompatibility might be visual changes. So have you ever, it just made me think of this. I like to drink hot tea. I don't know if any of you guys like to drink hot tea, but I was raised drinking my hot tea with cream in it, which is English tea. So one time I had a tea that was like really fruity, and it's the acidity of it when I put the cream in made the cream like in little white clumps. It was like it curdled the cream. And so sometimes this can happen when we mix medications together. We might get like white little floaties or particles, or what they call precipitate. There could also be bubbles, right? Or turbidity. So it could get kind of foggy, cloudy looking. All right, so that would let us know that these two medications probably shouldn't be mixed up. There could also be chemical changes that are not visible. So the quality or the potency of the drug could be degraded. And then this could make the medication toxic for the patient. Instability is another example of a sign of incompatibility, which means that the stability of the mixture can be influenced over time. Exposure to light, temperature variations can also contribute to that. And then therapeutic incompatibility. So if a patient is taking a certain regimen of medications and we add this medication, it could cause an adverse effect because it could interfere with the other medications or have an adverse reaction. So some things that we always want to do, stand by. Here we are. So some safe medication practices that we want to make sure that we are aware of is that anytime that a medication is mixed, like I said, we need to anticipate or consider the possibility that there could be an incompatibility. We also want to read the manufacturer's instructions really carefully and follow the strictest set of guidelines. So if we're looking at federal laws, state laws, local laws, agencies, facilities, policies, and procedures, we want to follow the guidelines that are the most strict and stringent. Another thing is that we always want to make sure that we practice sterile technique, right? And then accurately label, super important to accurately label. And if you are writing out a label, make sure that it is legible, because that's your communication piece to someone else if you're not present, right? And then once the drugs are mixed, even though we did a calculation of the dosage, we might have to recalculate the dosage according to the new elixir that we have created. Similarly, when we are reconstituting medications, we also want to make sure we're following the strictest rules. We apply sterile technique and that we recognize that the shelf life of a drug may be limited. So we want to check the expiration date of that, and also look at the manufacturer's instructions to make sure that we're not keeping that drug for longer than we should be. And then it may need to be stored differently after it's reconstituted. Again, correct and accurate and legible labeling, and then recalculating that dosage after reconstruction. Concentrating and diluting medications. So a lot of times medications will come in a glass vial, but they're in the powder form and they need to be reconstituted. And it does say on the vial like how many mLs and what it needs to be reconstituted with. Typically sterile saline is what they reconstitute thrombin with, dantrolene, what else am I thinking of? Antibiotics like Ansef or gentamicin or tobramycin or anything like that. They typically reconstitute that with sterile saline. All right, so that's going to reconstitute, and then diluting the concentration would be adding more of that sterile saline than is suggested, or increasing the concentration would be not adding as much as would be suggested. I don't know that we really do a lot of this out in the field. I'm trying to think if I've ever had any situation where I had to determine, increased concentration or increased dilution. Really can't think of a time where I've had to do that. There have been times where an example that comes to mind is one patient that I had in the past that developed a surgical site infection in her total joint replacement, and we had to bring her in and take out the hardware. And this isn't uncommon, where if there is some sort of surgical site infection where an implant is involved in a bone, then we're going to remove that, and until the infection clears up, we can't put implants back in there. So in this case and in other cases, some bone cement will be mixed up. So as the surge tech, you would mix up the bone cement, but instead of just using the powder and the liquid for the bone cement, powdered antibiotic like tobramycin or something like that would be added to the mix. And I know that's not increasing or diluting, but that's really the only thing I can think of where we're kind of combining things. And, we're really going to do what the surgeon tells us to do. So if the surgeon wants something added or deleted or diluted or whatever the case may be, then we're going to follow the direction of the surgeon. As always, thank you for listening. I hope that this was helpful and that it contributed to your learning. I know that a majority of it was a review. Don't forget to complete your critical thinking review questions that are found at the end of the chapter on page 32, and then go ahead and jot down any muddy points that you might have for when we meet in our next Zoom session. That'll be all for now.